Bismillahirrahmanirrahim. Assalamu alaikum. Dear viewers, I am Dr. Noshin Afshan and you are watching Dr. Noshin Afshan YouTube. I hope that all of you would be fine and I am thankful to you for watching this video. To watch more videos, please subscribe my channel and press bell icon. So our today's lecture is about organic chemistry and the specific topic is enantiomers. As the chirality is also closely linked with the enantiomers, so we will discuss about the enantiomers and chirality with special reference to their introduction, the properties, their examples and the optical activity. So now let's begin. So what are the enantiomers? First of all, the introduction of the enantiomers, in which we will study that what are the enantiomers or their different names, as enantiomers are also called as optical isomers as well as configurational isomers. So we will also see that why they are called as optical or configurational isomers. So enantiomers are such isomers that are non-superimposable mirror images. For example, यहाँ पे कॉन्सेप्ट है नॉन सुपरइम्पोजेबल एक है, दूसरा है मिरर इमेज. अगर आप हैंड को मिरर के सामने रखते हैं, then what will you observe? That its image would look like this, and if you place one hand on its mirror image exactly one above the other, then you will see that the front hand is not exactly the same as the second one, because here the thumb is on this side and here the thumb is on this side. So in what way we will say that the superimposable? When they are exactly the same from front and back, then we can say that these are superimposable. If these are not identical to each other, then we will say that these are non-superimposable. So in this way, here such compounds, for example, here this is 1-chloro-1-ethanol, because at this carbon one chlorine atom and one hydroxyl group is attached, and at the other end it is attached with the CH3 group and also with the one hydrogen. So in this way you can see that here this hydroxyl group, this chloro group, CH3 and hydrogen, these all are four different groups, and when you place it in the front of mirror, then its image would look like this. Chlorine is on this side, then chlorine would be on this side, and hydrogen is distant apart from this carbon. Here also hydrogen is away from this or is oriented along this position, and hydroxyl as above, so it is aligned as it is at the above of the or in the upward direction. So now you can see that you put this isomer and you take this isomer and put it on this one. Then here the chlorine is along the thumb, but in this compound along the thumb it is hydrogen. So in this way we can say that these are non-superimposable, and of course these are the mirror images. So the non-superimposable mirror images are called as enantiomers. And the central carbon, okay, here the property is one bond you will see with you will draw with the wedge line. Okay, this means the atom that is bonded here, for example here the chlorine, is directed towards the viewer. For example, this is the plane and the chlorine is pointed upward or towards the viewer, that is for example me. I am if I consider myself as the observer or viewer, then the chlorine would be pointed towards me. And with the dashed line, this group CH3 is pointed away from the observer or behind this plane. So this wedge, this is called as wedge line, and it is pointed towards the observer or above the plane. And the dashed line, that is represented like this one, as here it indicates the CH3 group. So this dashed line indicates the group attached is pointed away from the observer or behind the plane. So, but the other two that are pointed either along any two sides of the tetrahedron geometry, that are pointed with the solid lines. Because when you see the tetrahedral geometry, you can see that two groups are attached along the plane, but the other two groups are either one above the plane and the other one is behind the plane. So here we will draw these four groups in the form of tetrahedral geometry that would indicate the group that is pointed upward or towards the observer, drawn with the wedge line, and the other group that is pointed behind the plane would be drawn with the help of dashed line. So this is the introduction of the enantiomers. So now we see that why they are called as configurational isomers, because you can see that here the configuration is like this one. What is the configuration actually? It means the sequence of the bonded atoms. They are arranged or they are oriented in space, or in other words, this is 3D orientation in space is called as configuration. So in this case, the chlorine is attached on the, let's say, on the left side, and here the chlorine is attached on the right hand side. So in this way, the orientation becomes different. Okay, in these two isomers, the orientation of these groups is not identical as in this case. So on these basis, that when two isomers have the different configuration, we may say that they are configurational isomers. And the other example of these isomers are either S-ibuprofen and L-dopamine. So before we move ahead towards these examples, we just see its properties. So the properties of enantiomers or configurational isomers are: the enantiomers have the same physical properties. So what are the physical properties that would be the same? For example, melting point of the two isomers or that are enantiomers. Okay, so the physical properties would be identical. And what are those physical properties that are melting point? For example, boiling point, their densities. And the other point Okay, with reference to their melting point, boiling point and density, they would behave identical. Okay, these properties would be identical or almost same. The other property is they would retain the chirality or lack symmetry. So here there is actually a full concept. Let's move forward to that concept. What is the symmetry means and what is the chirality? So chirality is actually a property, but the compound or the isomer or the enantiomer is called as chiral. So what is the chiral compound? Such an isomer that is chiral compound. When we will say a compound as it is chiral, such a compound that consists of 4 different groups Okay, such a compound that consists of a carbon atom that is bonded with four different groups is called as chiral compound. For example, as the previous example shows, here it was attached with the hydroxyl group and it was attached with chlorine. Here it was attached with CH3 and here it was attached with, let's say this was chlorine and this was hydrogen. Okay, in this case you may see that here it is the hydroxyl group, chlorine, methyl and hydrogen. So this carbon is actually bonded with these four groups and this carbon would be called as chiral stereogenic center. Okay, this compound is called as chiral compound, but this carbon that is further bonded with four different groups is called as chiral center or stereogenic center, or also asymmetric center. So it may be termed with the three names as chiral center, stereogenic center or asymmetric center. And this compound is called as chiral compound. So what does this chiral compound actually represents? This chiral compound represents that they would show the optical activity. Such compounds that are chiral in nature would be optically active. So before going to the optical activity concept, we first say that if this is not bonded with the four different atoms, what would it is called? What would we say about that compound in which that is not bonded with the four different groups? That would be termed as a chiral compound. That is just a chiral compound. So, the achiral compound is such a compound that retains plane of symmetry. That retains plane of symmetry And what is the plane of symmetry? Actually, this is a plane that cuts a compound into equal halves or in two halves such that one half is the mirror image of the other half. So what is the plane of symmetry? That is such a plane that cuts a compound into halves. And those two halves would look like the mirror images of each other. And in that way, we may say that those compounds that would have the plane of symmetry would be called as achiral. So for example, okay, and that carbon because of which the compound would be achiral, that carbon would be termed as achiral center. And no doubt, no problem that if there are one or more than one achiral centers. For example, if you have this hexanone and the other compound, let's suppose it's H and CH3. This is 2-methyl hexanone, cyclohexanone, sorry, cyclohexanone and 2-methyl cyclohexanone. So the plane of symmetry would be to cut this compound into equal halves. If we cut it along this side, then the carbonyl group would be pointed along one side and the other side would not be identical as the first half. So if we cut along this side, along this direction, then the half carbonyl group would be along the first half and the other half would be along the other half. So in this way, this has been cut from the center of the compound, from that center which cuts this compound into equal halves. And as if we cut it along this direction or we cut it along this direction, if we cut it along this direction, we will see that this compound or this group is not along this on this side. So we cannot cut this compound in such a way that the one half is mirror image of the other, either from this direction, from this, or along this one. So in such a case, when we cannot cut the compound into equal halves, we may say that these are chiral, because here this carbon is attached with the 4 different groups, one methyl group, the other one hydrogen group, and along the other side the methylene group CH2 that is further bonded with CH2 and so on. And along the 4th side, this is attached with the carbonyl group. So these 4 groups are not identical: methyl, hydrogen, methylene and carbonyl. So these are the 4 different groups. In this way, on the basis of this carbon or chiral center, we can say this compound as chiral, and we may say that it lacks symmetry. It lacks symmetry or the plane of symmetry. And if we say this, then this half is identical to this half. So we may say that it is achiral or it has the symmetric. This compound is symmetric or it has symmetry. It has plane of symmetry. So now the chirality is linked with the lack of symmetry, that is this point. So that is so interesting that every line in the in these stereoisomers actually has a concept in it. But don't be confused that it's not really difficult, it's very interesting and very easy as well. So such achiral compounds are also symmetric in nature or they retain plane of symmetry. And the other example of these compounds is let's see, here it is attached with hydrogen. One, two, three, and four carbons, that is N-butane. So now see, either we cut it from this side or we also have said that such a plane that cuts this compound into equal halves would be the plane of symmetry. So either you cut it along this plane, it would also be the plane of symmetry, because here 4 hydrogens are attached and here also 4 hydrogens. Or in the other way, if you cut it along this side, then it is also here, this ethyl group is also identical with this ethyl group, but actually it is cut in such a way that 2 halves are mirror images of each other. So in both ways we may say that it retains plane of symmetry, so it is achiral. But if we change this hydrogen or any hydrogen with the other group, for example, we change it with hydroxyl group. So now, is this compound retains the plane of symmetry? No, that would lack the plane of symmetry, and in that case, as this would be stereogenic or chiral center or chiral carbon, on this basis we will say that it is chiral in nature, and also it would assist in the formation of enantiomers